Today we'll be talking about intramolecular forces and potential energy in covalent bonds. Why do covalent bonds form in the first place? The formation of covalent bonds has a lot to do with energy and a lot to do with the various forces that have a tendency to draw atoms together or push atoms apart. These forces between atoms are called intramolecular forces. Intramolecular means that they happen inside the molecules. These are the forces that bind atoms together to make a molecule or compound. In the future, we'll be talking about intermolecular forces. These are the forces between molecules, and these are something that's very different. So, with intra, think A for atoms, the forces between atoms. Before we talk about these forces, I want to talk about electric potential energy. Just like there's potential energy with gravitational forces, and you probably learned about this in physical science or in physics, there's also a type of electric or electrostatic potential energy between two charged particles. This is closely related to the Coulomb force. Say you have two atoms that are floating out there in space somewhere in gaseous form. We're going to call these two atoms a system. A system is a particular set of things being studied. Our two atoms are our system. Atomic systems tend to be most stable when the potential energy is the lowest. And when we say low, we mean negative. We'll look at some graphs in a minute. This energy is very much related to the forces that are going on between the atoms. So let's think about these forces in more detail. As the atoms get closer together, their electron clouds begin to interact with each other. These interactions affect the potential energy in the system. Some interactions increase the potential energy, and some decrease it. One of the things that increases the potential energy is the interaction between the particles in the atoms that have the same type of charge. As the atoms come closer to each other, the positive nuclei in these atoms repel each other. The electrons in these atoms are also repelled by the electrons in the opposite atom. These repelling forces tend to make the potential energy of the system increase. An increase in potential energy makes the system less stable. However, there's another force that happens at the same time that decreases the potential energy. The electrons on each atom are attracted to the nucleus of the other atom. The attractive force tends to make the energy of the system decrease. The reason that bonds form is that the atoms are more stable when they're bonded together than they are when they're apart. Bonds form in such a way as to make the potential energy in the system as low as possible, since low potential energy is what makes the system stable. Atoms don't want to get too close to each other, or else the repulsive forces will take over. They don't want to get too far from each other, since the potential energy will try to pull them back together. There's a distance between the atoms that is just right, and this will eventually be the length of the bond that is formed. One way we can look at this phenomenon is to examine a graph where potential energy is on the y-axis and the distance between the nuclei, also called internuclear distance, is on the x-axis. You can see how when one atom moves an infinite distance away from the other one, the energy is zero. And that makes sense when you think of Coulomb's law. The bigger the distance, the smaller the force, and since force is very closely related to energy, the smaller the energy. As atoms come closer to each other, the potential energy decreases. It becomes negative. Low energy is what makes it stable. But there comes a point where if you go any closer, the potential energy starts to go up again, and that's because the repelling forces between the two atoms become stronger than the attracting ones. Moving atoms too close makes the system unstable. So the most stable distance is the one with the lowest potential energy, and that's right here, at the bottom of the dip where the energy is most negative. This point on the x-axis where this happens is the bond length. It's the length of the bond that forms between the two atoms. This is how far the nuclei of the atoms are apart. Bond length is often reported in angstroms, and 1 angstrom is 10 to the negative 10th meters. We call the difference in energy between 0 and the bottom of the dip the bond energy. Energy is always released when new bonds form, but in order to break bonds apart, you have to put in energy. It takes the same amount of energy to break a bond as was released when the bond was made. For example, when hydrogen and chlorine gas come together to form a bond, 432 kilojoules per mole of energy is released. In order to break that bond, you have to put in 432 kilojoules per mole of energy. Once again, bond energy is the amount of energy we have to put into the system to break the bond apart. Different combinations of atoms will have different bond lengths and different optimal potential energies or bond energies. In this particular diagram, we have two different molecules containing nitrogen and hydrogen. You can see that one of them has a lower potential energy and also a shorter bond length. There are two main factors you need to know about when you're trying to compare bond length and the bond energies in different molecules. The first thing is bond order. Bond order is the number of bonds between the two atoms you're looking at. Single bonds are the weakest. They're pretty easy to break. Double bonds are stronger than single bonds. They're also shorter. Triple bonds are stronger than double bonds and single bonds. Triple bonds have the highest bond energies, and they also tend to have the shortest bond lengths. So let's look at this diagram again. This diagram is looking at the bonds between nitrogen atoms in the two different molecules. In the first molecule, the two nitrogens in the molecule are bound together by a single bond. But in the second, the nitrogens are bonded by a triple bond. You can see that the bond length is shorter for the molecule that has the triple bond. There is also a bigger energy dip. This bond is strong, and it takes more energy to break it. The other thing that affects the bond length and the bond energy is how large or small the atoms are, how large or small the atomic radii are for the atoms you're looking at. As the size of the atomic radii increases, the bond energy decreases and the bond length increases. It requires less energy to break the bond. As the two atoms get larger, the region of space in which the electrons are shared between the two atoms becomes smaller. You can see this in this example. The overlap between the valence orbitals of hydrogen and fluorine is pretty large. But in hydrogen iodide, it's smaller. Iodine has a larger atomic radius than fluorine does, and there's not as much overlap. The bond is weaker in the hydrogen iodide molecule than it is in the hydrogen fluoride molecule. The bond in the hydrogen iodide molecule is also longer. We see something similar with these diatomic fluorine and diatomic iodine molecules. The overlap between the valence electrons is larger in the diatomic fluorine molecule than it is in the diatomic iodine molecule. The covalent bond is also stronger in the diatomic fluorine molecule than in the diatomic iodine molecule. This factor of bond size means we see something interesting in terms of periodic trends as far as the bond length is concerned. Bond length tends to decrease as you move across the row of a periodic table. This makes sense since atomic radii are getting smaller. Bond length increases as you move down a column. This also makes sense since atomic radii are getting larger as you go down. Bond length is actually an average distance between the nuclei. That's because the nuclei aren't static, they vibrate. You can model it as two balls connected by a spring, stretching or compressing and going back and forth around some sort of equilibrium position. You can think of a bond as being kind of like a spring, with the bond length being the midpoint of the oscillation. If you stretch it, the potential energy goes up, and it wants to get back to that equilibrium position. If you compress it too much, the potential energy also goes up. But there's that place in the middle where the energy is just right. Now let's look at a couple problems. Say we have the following diatomic molecules: carbon, silicon, and germanium. Which bond is the strongest? Pause the video and see if you can figure this one out. All three bonds are double bonds, so bond order isn't really going to be a factor here. We need to look at size. From the periodic table, we can see that carbon is the highest up in the periodic table, so it's going to have the smallest size. Therefore, the carbon bonds are going to be the strongest. Which bond is the longest? Pause the video and see if you can figure this one out. Germanium is lower in the periodic table, and it will have the largest radius because it has more shells or energy levels. So the bonds between germanium atoms are going to be the longest. Here's another problem. The graph below shows the potential energy as a function of internuclear distance for molecular bromine and for an unknown heteronuclear diatomic molecule, which we'll call AB. Based on the data in the graph, which of the following correctly identifies the diatomic molecule AB? Pause the video and see if you can figure this one out. Here's a hint. The diatomic bromine molecule has a single bond. When we look at the graph, we see that the molecule AB has a longer bond length than diatomic bromine does. It also has a lower bond energy. Since the molecules with double bonds tend to have shorter bond lengths and higher bond energies than molecules with single bonds, we can rule out carbon monoxide and sulfur monoxide, which have triple and double bonds respectively. That leaves iodine monobromide and hydrogen chloride. The atoms in hydrogen chloride have smaller atomic radii than those in the molecular bromine. Therefore, the bond between hydrogen and chlorine would be shorter, not longer, than the one in molecular bromine. The only one left is iodine monobromide. Iodine has a larger atomic radius than bromine, and that larger size is going to make the bond longer and also weaker, with lower bond energy. So iodine monobromide is our answer. Now you should know about intramolecular forces and how they lead to covalent bonding. You should also understand the important role that electrostatic forces and potential energy play in bond formation. You should be able to interpret a graph of potential energy versus distance between atoms. You should be able to identify bond length and identify where potential energy is lowest and explain bond energy. And you should be able to explain why some covalent bonds are longer than others and why some covalent bonds are stronger than others.